Today I want to go over the problem named task scheduling. So sometimes we have some problems, we have some tasks, and we want to schedule them in return the order of the task in the schedule of all the tasks. Also, we have course schedule, similar names, or we have, let's say, events, any events. So let's say event can be course, can be a course, can be a task, can be a job, can be a process in the the operating system in our CPU. And the problem is actually the objective is to find a sorted a schedule for all of these tasks. And what is the given? What is our assumption? Actually, if we don't have any assumption, we can return in any order, right? We can, let's say we have n tasks, we can return in any order. But we have some assumptions, and like the given is some dependencies between tasks. Let's say we can say the task A is prerequisite to task B. Okay, we can say task A or course A is prerequisite to task B. I'm writing in task A is prerequisite. Let me, I need to auto, okay, I want to have this here always. Okay, prerequisite is prerequisite to B. It means that we cannot run task B before A. A should be finished, and then we are allowed to do the B, right? Or we can say that B depends on A. So we have this kind of dependencies. Maybe for some of you guys, if you joined for my first meetups, I was doing in Hacker Dojo, the first problem is repetitive for you guys. But I think this pattern is really really common, and and really practical even in real projects. We use this problem. We have lots of real scenarios that we have some dependencies between different tasks, different events. But after I solve the basic problem, I will go over one hard problem. You can wait if the first problem is repetitive, and the second problem will be more enjoyable for the people who joined the first meetups in Hacker Dojo. So the given is list of some dependencies, and let's say when we say A is prerequisite of prerequisite of B, we can use this as a list like this. AB means the dependency we talked about it on top here, right? It means A is prerequisite of B, and we can have different several dependencies. Let's say also B is prerequisite of C, and C also B is prerequisite of D, and let's say C also is prerequisite of D. And we have our input is all of these guys, and we name these guys as dependencies. A list of pairs, or list of lists, or if we talk about it based on array, it is array of arrays, vector of vectors, right? So let's go and talk about all of these dependencies and show all of them graphically, right? Like we did here. So A, when we say A is prerequisite of B, and then we say B is prerequisite of C, it means that I will have another edge like this. And then B is prerequisite of D, so it means that I have this one. And also C is prerequisite of D, so it means that I will have this guy. So what is the type of this data structure? How we can model all of these dependencies? Which data structure is the best to model all of these dependencies? Any comments? Any comment, please? I want to have a little more.
The graph, maybe?
Yes, the graph. And as you can see, we have direction in our edges, right? We have two types of graphs, right? Undirected graph, or unidirectional, or directed graph. As you can see here, dependencies, we have directions. So the best data structure to model our problem, actually the assumptions of our problem is directed graph. Means all edges has a direction. Okay, so far we learned that we can convert all of these dependencies to a graph, to a directed graph. And why we do this? Because if we have a graph, we will traverse whole of this array once, and we will create our graph, and then we know each node, all the neighbors of each node. But if we don't build the graph, every time, for example, if you want to find all the neighbors of B, I have to traverse whole array to find all the neighbors. But if we do this for one time, and then we will have all of these guys. And how we can implement? Right now, we detected that we need to use directed graph. And how many types of implementations we have for a graph? I think most of you guys know maybe. We have two general methods of implementing a graph. Can you give me an answer? Any one of you guys?
Adjacency list.
Okay, adjacency list. Adjacency list. Also, we have another method also.
No.
Mm-hmm.
Matrix.
Matrix, right?
Yeah.
Yes, adjacency matrix. So we know that in our undergrad courses we had all of us I think we had adjacency matrix is like we have 0, 1, 2 over let's say n-1. Let's say we have n nodes or n vertex in our graph, and we use 0 or 1. 0 means we don't have any edge from 0 to 0. 1 means we have an edge from 0 to 1, and we will have some binary values here, and we know all the neighbors, right? But in adjacency lists we have another thing. We will say we have 0, and let's say I think my 0 is okay. We have a 0, and we write all the neighbors of 0. And for this example, I want to change this to A. Let's say we have A. What is all the neighbors of A is only B, right? So we have a list of neighbors. And then B, what is all the neighbors? C and D. And C, all the neighbors is D. And what is D? All the neighbors, it doesn't have any neighbor. Actually here, the neighbor means, we can say the next node. Because we have directed graph, it is not symmetric, okay? So, and this is adjacency list, because we have a list of all adjacents for each node. And I wanna, in interviews, usually in interviewers ask you why you are selecting adjacency lists. What is the reason you are using adjacency list rather than, adjacent matrix or vice versa? Actually, one of the basic reasons is that, if our matrix is really sparse, it means that we have, really low number of, the ones. It means that we have less number of edges. We don't want to, spend, whole matrix, because we don't have lots of edges. and we prefer to use adjacency lists. This is one of the typical answers. And another thing is, actually working with adjacency lists usually is easier. Here also, let's say, in the adjacency matrix, again, if we want to find, all the neighbors of 0, we need to traverse whole row to extract them. But here, in the adjacency list, if we want to find, all the neighbors, I have a list. I have already calculated. Depending on the nature of the problem, we will detect which one is better. And for this problem, definitely, we have dependencies. In most cases, we can say that, we can claim that, the number of edges are not so much. It means that the matrix is sparse, so it's better to use adjacency lists. And what is the data structure for implementation of this, this structure? Which primitive, which data structure I can use to implement this structure?
So we could use a dictionary of lists, I think.
Yeah, a dictionary, or in general way, we can say we can use a hash map, right?
Mm-hmm.
Yeah, in different languages, in different some languages we say dictionary, in some languages we say hash map, but the general term for dictionary is hash map, and hash map has key and value. It means, it maps some keys to values. And if we use this of our adjacency list or our graph, will be a hash map, and the key will be node number, and value will be a list of adjacents, right? A list of neighbors. So the reason I'm going in a step by step, because this problem is really, comprehensive problem, because it can evaluate the candidates, all, the knowledge of the data structure, even the implementation of the, the data structures, how you can define, how you can, implement the graph using a hash map. And I'm going step by step for people who maybe didn't see this kind of problem before. So we use a hash map for to model our graph. Okay, so far we know how we can model this. And so let's say we want to solve the problem. We have this guy, the graph, and we want to find an order, find scheduling to run all of these guys. So what will the first step? Which task I can select initially. So I cannot select D, right? Because D depends on C and B. I cannot select C also, depends on B, and also B. The only task I can select is A, because it doesn't have any dependency, it doesn't depend to it. So I can select A. So the first step, I will select A and I will put in the output. I'm selecting A, and then I want to remove this and all of its dependencies, all of the edges of the A, okay? Because we scheduled it. And then second run, B, C, D, which node doesn't have any dependency? B, right? Right now, B doesn't have any dependency because we scheduled A. Right now, B doesn't have any, so I can select this. And then I want to remove this and all of its edges. And the next round, which one can be run? C, right? Because D depends on C. I can select C and I will delete it. And the last round, D can be selected. And this is my scheduling. Actually, we will say, okay, we have to run first A, and then after A will be finished, B, C, D. And we want to return this guy, a list of our scheduled numbers, okay? So let's go back, let's back to my manual, solving. how we did this, how we worked based on how we solved, the problem. First of all, we detected which node is doesn't have any input degree, is A, right? And then when we removed it in the second run again, we want to find which node doesn't have any input degree. So any node has some input degree and output degree, and so we need to detect which nodes are 0 input degree, and we name them as source. In network, actually, we name these guys as sources. A source is a node that doesn't depend to any other node. So in order to detect the nodes, I need in degree of all nodes. So it means that in order to implement my algorithm, I need another. So far we said we need a hash map to define our graph. Also, in order to deploy my manual algorithm, we solved this. We figured out that we need to know the in degree of nodes, right? So let's say we calculate in the first round, calculate the in degree also. What is the in degree of 0 is 0. Actually A. What is the in degree of A? I'm assuming this is the index 0, 1, 2, and 3. Okay, so the in degree of A is 0, and in degree of B is 1, in degree of C is 1, and in degree of D is 2. So in the second step, based on our simple example, we detected that we need in degree array or list or vector, okay, to keep all the in degree values. So when I'm deleting this guy, I need to update the in degree of all of its children, right? Let's say I'm deleting the A, I need to decrease the in degree of B. So I have to update this guy to 0. And because it is 0, I know that B is my next source, right? It will be my source node. So far, this is the, the process, the strategy to solve any problem. First, based on the assumptions, you will detect that how to model that. We had some edges specifying the dependencies of, n tasks or events. And we detected that we need to have a hash map to model all of these edges as a graph. And then, based on a simple example we solved here, we detected that I need an in degree array to keep all of the, the in degree of each node, okay? And after this, we wanna talk about, which approach we need to solve the problem. When you have a graph problem, you should think about DFS or BFS. We have 2 candidates. And sometimes, or actually not sometimes, most of the times, both approaches are working for lots of problems. It depends on you that you are comfortable with DFS or BFS. DFS is actually the recursive approach, and BFS is a queue-based and iterative approach. And usually when for me, as it is, only my favorites, I don't recommend, anyone. Some people I saw, they are really comfortable with, recursive solutions. But for me, I really love, the queue-based and BFS solutions if I have a graph problem. I think, maybe I solved more problems using the iterative and queue. So that's why I want to go over BFS, but definitely you can use DFS also. So let's go and after you decide, in the interviews also, you have to decide at first, I want to use recursive or iterative, DFS or BFS. And after you decide to use one of them, don't doubt it. Continue and try to solve based on the approach you selected. If you doubt your approach and go and back between your BFS and DFS, you will you will miss that round of interview, definitely. But sometimes we detect one of them and we try and we see everything is going so harder and getting so harder and harder. It means that we selected really the the bad, we didn't select the best approach. But you should detect that in the first 1 or 2 minutes, not after 10 minutes, right? If you see, for example, you selected DFS and you need to do lots of extra things to formulate your problem using DFS or recursive, you should rethink about the approach. But after you're doing the first 2 or 3 minutes about your approach and you selected the best one, don't doubt it and go over it, because it is really killing that you wanna doubt your approach in the interview. Okay, so right now I want to go over I want to use the BFS and using the queue, because as you can see here, we selected A, and the next round we needed to have also the sources. So when we want to use a BFS, the first step is to detect which parameter, which variable is the most critical one in my decisions. And here, as you can see, the sources are really important for us. Source means the nodes with 0 in degree, okay? And we don't want to talk about the out degree. We are only talking about the in degree, input degrees. So it means that I can, let's say I have a queue here. Let's say, I think I have to change the color. Let's say we have a queue. And in the first round, based on in degree, I detect that. Let me write here also in degree. 0, 1, 1, 2. I go over in degree and find the sources. The only source is the first one, which is A. I put here, and this is my queue. And you know that you have to be really fluent in the BFS pattern. We have, while, the length of queue is greater than 0. It means that in the first step, we append all of our sources. Right now, we have only one source into the queue, and then we go over, our while queue, which is our, the body of our, the algorithm, okay? And we know that in the first step, we pop the first element, which is A here, right? If I pop this, let's say I pop this, and this is my source, and I will put this in the outputs. Pop this, and then in the second step is insert it to the result. As we did here, we'll say A will be in the outputs, okay? So what is the second step? I wanna add the new sources maybe we will have if we remove A or if we schedule A. So in the third step, I have to update in degree array. How can I update the in degree? I will decrease all of the all the children of A, because we removed it. And let's say here we removed A, and it has only one children or one neighbor. I have to decrease all the in degree, all of the neighbors in degree. So we know that how we will do this, how we will do the updating the in degree. And maybe we will having some new sources. For example, here, if we remove A and we decrease B in degree of B to 0, we will have 0 and 0. And now we know that the second task or event is a new source. We have to append the new sources to the queue. So we have to append right now, you know, for example, I will append here. And again, so we append this, and then the second, you know, the next round, let me, so this is, you know, the whole body of, you know, the BFS algorithm, okay? So, and we have a queue. So the second run, you know, we will pop again the first element of V, element of Q. So I will pop the B, and then I will, in the step 2, I will insert it into the results. And then I will update how many children we have. We has, you know, 2 children, right? So I will change this to 0, and this will be 1. So I change, you know, 1, and because B has 2 children, and because I'm removing this guy, C, the in degree of C will be 0 and D will be 1. So C also is a new in the step 4. We will add C in the queue because it is a new source, and I will add C here. Again, we will go over, you know, the second round of, you know, the third round of the queue, our while loop. We will pop C. We will put in the output in the second step. We will update the in degree. If we remove C, we will remove, you know, its edge also. So it means that the D or the last node's in degree will be 0. So D should be added in the queue. In the step 4, we will add in here. And in the last round of while loop, because we have something inside of the queue, right? We will pop it, and we will add this in the output. We in the step 2 and update it in degree. So I did this. It doesn't have any children, so we don't need to do anything. And also, we don't need to add any new sources because we don't have any new source. And we will pop. Actually, we popped in the first step, and in the last round, len of Q is 0, so it will be done, and we have the result, and we will return it. As you can see, this is the a BFS pattern. But why we name this as a new pattern, and we name this pattern as a topological sort? Because it is a little different. You need to build your graph, and your queue will be fed with some different, concepts. If you remember, in the binary tree BFS traverse, we added root in the queue, and then at each step we popped the first node, and we added its children, right? Or here, we don't have. It's not children. We shouldn't, add all the children. We should add children if they are sources. If we have some conditions, it is not as simple as BFS traversal of a binary tree. We need to, and the queue only keeps the sources. It doesn't keep all type of nodes. Okay. So topological sort is really one of the important patterns. Usually, you will see this kind of problems in on-site interviews, unless they ask the basic problem, which is this one. Also, I didn't see the topological sort in the phone interviews in the great top tier companies. Maybe when you do the interviews for startups or small companies, maybe they will ask. But usually in the interviews at top tier companies, they don't ask this kind of problems. They go over the simpler, because it takes lots of time for most people to write the code of this problem. But if you are fluent, you can do this really fast. So now you have the algorithm, right? Only we have to dive in, the implementation. If you have any question, any comment, please ask. If you don't have, I will go over, the implementing all of these steps. We talked about it. And in implementation also, I usually teach how you should implement. You should make it as possible, as much as possible modular design. You don't need to dive in all the codes. You have to build some blocks and then call them. And it is really helpful especially during the interviews. You save your time. Any question, any comments so far? Let me check here. Let me check the chat. We have one more. Okay. Any comments? Okay. So let's go and implement the algorithm. And after this, we will go over a little more, a harder problem based on this pattern. And I think that would be enough for today meetup. Okay. Let's go and start our implementation. So first of all, we know that for BFS, we need a queue, right? We need queue. In any language you are, working, depending on your language, you have to know how you can implement the queue. But in Python, we need to use the dequeue from collections. We need to import dequeue. Dequeue is actually a double linked list, and it means that we can add or remove from the beginning of the list and also the end of the list with the order of 1, constant time complexity. And it means that in other languages you should use a double linked list if you don't have dequeue, exactly this term. So, and let's go and define our topological sort. So what are the inputs? Let's say we have n, which is number of nodes or number of tasks. You can map this problem for to the lots of the real problems. And we have some edges, which are our dependencies. We talked about it. Edges is a list of pairs that we have. We have all of the dependencies over there. And so we want to return, first of all, I want to define my results, because we want to return our, a schedule in the results. And let's say, and also you have to check first, some edge cases. Let's say if n is n is less than or equal to 0, so we don't have any scheduling, right? So return result, which is empty list. So this is only the edge case. And what was the first step? Do you remember? I was talking about it. The first step number 1 was building graph and in degree. Because if you remember, we said in order to model our problem, we need a graph and in degree. So and now you can write the code to build them, or you can assume that you have a function that creates the graph and in degree for you. Okay, and this is the part that's I strongly recommend you assume that and write the main part of your algorithm. And if you have time, you will go and write that function also. Okay, so I'm assuming I have a function named build graph, and it returns me the graph and in degree. And fortunately in Python, it is really easy to return, several, variables. And in other languages, if you can, return, some output, variables in the input arguments. But here, the Python is really easy to handle this kind of several, the output result values. So let's say I have a function and it returns me graph and in degree. You can assume that, you have a function and the name is build graph. And in order to build a graph, I need to pass n and edges to build my graph. Let's say if I call this function, I will have a graph which is something like this, 0, 1, 2, and we are assuming edges are the number of the tasks are starting from 0 to n-1 to make it easier. Tasks are, numbered from, let's say tasks are numbered from 0 to n-1. It means that, my graph is something like this. And for each of these guys, we have, some, adjacency lists, right? And also we have a in degree, which is a matrix, which is an array, which is a from 0 to 1 to n-1. Okay, I'm assuming I'm creating, all of these guys inside of the build graph. I saw lots of people go and dive in and building the graph. I strongly recommend assume that you have that and go over, if you know the approach. If you don't know the approach, yeah, you can do, build a graph. If you are fluent, at least you are showing that you know how you are creating data structures, how you are defining the data structures. But if you are sure that you know the approach, dive into the approach because that's the main part. So this is the first step. What is the second step? The BFS part, right? And for BFS part, what was the first step? Defining the queue, right? Defining the queue, and then go over the while loop. So it means that right now I need to define my queue. So my queue, as if you remember, we said our queue keeps the sources. That's why I wanna define, okay. I wanna define my, the name of my queue is sources, which is DQ. And this is empty at first. And I wanna, in the second step, let me add this here, define and initialize the queue. So what will be the initial value for a queue? Initial items, all the sources, right? All the sources in our graph will be I have to push all of them, append all of them in the queue. So that's why I need a for loop over in degree array. So I will go for, let's say for task. I'm assuming, they are task, but you can put, any node, doesn't matter. The name is not important. Let's say for task in. So we want to go over in degree, right? For in degree, so I will go over in degree for task in degree. So task will be the index of, and we assume that the index is exactly the, there is no mapping in a spatial mapping. 0 means in a task number 0. Okay, I will go over there and I have to check if the in degree of this guy is 0. If in degree of this guy or task is 0, it means that it is a source, right? I have to append this inside of the sources. I'm appending this guy inside of the source. Let me bring something under my hands, because writing in the bottom parts are really difficult when you don't have any under your hand. Okay, so we created our queue. So this part is actually this part is exactly defining a queue and the initialization of that. Okay, so what would the after this we have to go over our main part of our algorithm, which is while sources, and our queue name here is sources. When I'm writing while sources in Python, it means while we have any element inside of that. When it is empty, while will be, the sources will be false, and we will the while loop will be finished. So what is the first step in a while loop is to pop left or pop the first element. So I'm writing here, the task will be equal to sources that pop left. Pop left means, pop from the beginning of the queue. And now this task should be added in the results. We talked about this right here, right? I did the first step. Right now. I popped this, and now I want to insert it into the results. Okay, let's go ahead and do this. I will write result that append task. Okay, we appended this. And what is the next step? Update the in degree. I want to update in degree. How can I do that? Let's say I have to find all the children of task and decrease in degree of all of them. So it means that I need a for loop, right? And I know that if I go over my hash map, which is graph or my graph, in the index of task, I will have a list of all of its children. So that's why I will go over for, let's say the child, I name this as a child, in graph task. So we know that the graph task is a list of children of the task. So the child will go over one by one in all of them. What will be the first step? I will go and decrease the in degree of child. I will decrease this by 1. Okay. Also, we have another thing here, right? Update in degree, append the new sources to the queue. We have to check if this child is a source. We have to append this in the queue. So I will check if it is source. How can I check if it is source if the in degree of this guy is 0? After decreasing that, I have to write if in degree of child is 0, it means that it is a child. So I have to append, actually, sorry, it means that it is a source. Let me write here. Child is a source, right? And let's say I have here. So I have to append this inside the sources. So let's append child, because this is my new source. So that's it. We did this. It is, as you can see, it is so similar to the BFS traversal of the binary tree, but we need to build our graph at first. That's why I'm writing this as a function. If I wanted to dive in, creating the, this one, it will be so crowded, and people think, the problem is really difficult, but actually it's not. If you are fluent in building a graph, creating a graph, so it will be easy. And you can assume that you have a function that I will write this function in the next step, but you can assume that you have that. And the only difference we have here, for Q, we put all sources. We don't simply append the root, similar to the binary tree. Here we can have more, as the initial step, we can have more sources. So we need a for loop to append all sources in the queue. And but this part, the while, we have popping from the queue, appending in the result, and we need to add any new any new sources. But in the binary tree, we added the left child or right child. But here we need to check all the children. If they are source, we have to append inside of the inside of our queue. Let me silence my cell phone. Okay. So at the end, we have to return result. But there is something, some bug in this code. I intentionally go in this way. I want to ask you guys, what is the problem with this code? Everything is correct, you guys? Any comments? Definitely there is a bug in this code. I didn't talk about it. I want to only have a little more interactive session, actually.
So I have a question here. Maybe that's the bug. So in the for task in degree, don't we just check if task equals 0, because we already take out the tasks from in degree in the for loop?
So you mean this part, right? In the for loop for in degree, right?
Yeah.
So can you say it again? I didn't get your point exactly.
Yeah, sure. So we have the for loop over the tasks. So we already take the tasks out of in degree with this loop, and then we have the condition if in degree of task. Shouldn't it be just task?
No. Actually, task is in the index of this guy, right? But we have the in degree of all tasks here. In degree, right? We have to, in degree of task is actually
the for task in range something. If we take for task in degree, get index.
Yeah, I know. I got your point. But here, I made this problem easier. We don't have any mapping between index and we don't have any label for tasks, right? Mm-hmm. Right now, the index can be used as a label of the tasks. So let's say if you have tasks from A to Z, right? We have to map A to 0, B to 1, right? But right now we don't need that, because index is exactly this the task, right?
I'm not so super familiar with Python, but maybe I understand this wrong. But if I make the for loop for tasks in degree, doesn't it take the values then for task out? But if in degree has, like, for example, 0 or 1,
okay. I got it. Yeah. I got your point. Yeah. I think it is. Exactly. Thank you. It is my, I think typo. Yeah. Because, we say in the, exactly, we say in degree, task is exactly the value, right? Yeah.
Yeah. Right.
Yeah. Thank you.
Okay.
So, but, we have another, error, actually it was, we have some, actually, let me make this, a little more readable code. I think, it's better to write here. Let me in range, because, it will be much more readable. And then I think I prefer to go in this way because it is more readable, for people. Okay, so we go over indices, and then, we have to find it. Okay. So we have a really, big mistake, not big mistake, actually. We didn't consider some, go ahead.
Sorry, I just came, but it looks like if we are we dealing with cycles here?
Yeah, definitely. Yeah, that's the point. Yeah. If yeah, thank you. Right now, based on the simple example, we didn't have any cycle, right? If you have a cycle, what will be the problem right now here? Let's say I have, this, that's exactly the point I was looking for. Okay. C, D, in this, let's say, we have this cycle, our graph is like this. What really happened in this code? I will go over A, I will remove it. I will put this in the queue, right? A, I will remove it. And then which one is the source? No one, right? Because what is the in degree of B is 1. What is in degree of C is 1. What is in degree of D is 1. When I remove A, in this part of the code, for child of this, A's children is in B, right? I will check for all of these guys. I will decrease this from 2 to 1, because initially the in degree of this will be 2, because we have 2 in degree, right? It will be 1, and it is not 0, so I won't append it. And that's it. And the second run, sources is empty, because we added A and we popped it, and it is empty. It means that if we have a cycle, the length of our result will not be n, right? Or I can say in another way that we don't have answer for all dependencies. Sometimes the dependencies are, if we have some cycles inside of the dependencies, we cannot schedule all tasks. So that's why I have to handle that. After while loop, I have to check the length of result. If it is equal to n, it means that I could schedule all tasks. But if it is not equal to n, which is the number of total tasks, it means that we had a cycle, and I have to return empty, not the A, for example, in this example, right? So
Just
go ahead.
Yeah, so that's one way, right, to detect. Maybe maybe another way I've seen is that we keep states of the nodes, like visited, not visited, and visiting. And if we reach some node that is in the visiting state again, then
Exactly.
okay.
Amazing. You can, in all graph, problems, actually, when we have a binary tree or tree, actually, because we don't have any cycle, we don't need to use, visited matrix, visited array, or, let's say, the scene array, right? But when we have a graph, we need that. But this problem is easier than that. We don't need to use extra, space, because at the end, we want to detect that we had, cycle or not, right? So I think it is much more easier to write here if len of result is not equal to n. and after the while loop, we will say, this is the same, level, okay? If it is not equal to n, it means that we had a cycle. And sometimes the questions say, do we have any valid topological sorts for this dependencies? I can return here, return false. And at the end, I can return true. But right now, we want to return, the order, the scheduling. I have to return empty because we want to show that there is no valid scheduling for this dependencies. And if not, if it is equal to n, I have to return results. That's the really important part. And if the question is fine, if we have topological sort or not, you can return here false, and here you can return true. Okay, and that's it. The only part I have to implement is the build graph function. And if you don't have any question, I can go and build that one, and then we will go to the next question. Any questions so far? Okay. Let me erase all of these guys to have a little. Okay, so let's go and build the graph. If we have n, the number of nodes and edges. I want to define my function. And usually in the interviews, if you do this, in most cases, interviewers say, okay, you don't need to implement this function. If you do really well in the main algorithm. So I want to define build graph. N and edges are my inputs, okay? And so we want to create two in-degree and graph, right? And as I said, the graph is a hash map. Hash map in, Python, we use braces. The brace for, let me change move my cursor. So the graph will be, I want to put, I, which is the index of my, node. And the value initially is empty lists. I want to have this for I in range n. So in this line, I'm creating a hash map like this: 0, 1, 2, n minus 1, and all of them initially are empty. This is an empty graph. And then I need to define my in degree. In degree is we can use an array. Actually, I talked, here, I used an array, right? Because we are assuming that we don't have any label for our nodes. But if we have any label, we can use a hash map also. But here I want to go over. It will be. I think that will be much more better in order to have a general solution, because for example we can have let's say let's do this also with a hash map, but the hash map will be I and 0. Actually we can use definitely an array. Let's do this because it will make it more flexible if we have let me write this here for I in range. So it means that also for this in degree we have 0, 1, 2, 2, n minus 1, and all of them are initially 0. So this is my graph. This is my in degree. Okay, but we could use it in a simple array also. Okay, so we have the in degree, and what is the next step? I have to go over edges and create all of the adjacency lists and in degree. I want to write for edge, but we know that in edge we have parent and child, right? That's why I want to write here for parent, comma child in edges. I know that each edge has, different, some number of, the edges, and each edge has, 2 elements. And I know that the first one is parent, and this is a child. That's why I'm writing, here, parent and child. It is much more, easier to do this in form. So in the next step, I will write graph of, I want to add child in the list of parents. So I will write graph of parent dot append, because it is an empty list initially, right? Append child. Also, I need to increase the in degree of child because it has a parent, right? So I will write in degree of child +1, because now it has a pattern, a parent. And that's it. After this, at the end, we have to return in a list graph. The first one graph, and the second one will be degree. Actually, this is the easiness of the Python. In other languages, you have to define types and this kind of stuff. And as you can see here, we are, it's just, traversing the edges. And for each first element, which is parents, we have to add all the children in its adjacency list, and then, increase the in degree of the child. And if we have this, so I'm assuming, because we have in degree as a hash map here, I think here we will go over the task. It was a right now. Let me. Yeah, it is. I think, because here, because we have, yeah, it's true. Doesn't matter, because we know the keys are from 0 to n-1, and that's it. So what is the time complexity? Let's go over time complexity. Any answer for time complexity?
V plus E.
V plus E, yes, definitely, it's true. And I saw some people are struggling when they have graph problems to find the time complexity, because they go over, the code. But if you think about your algorithm, even without thinking of the code, and right now in this code, we traversing all nodes once and all edges once, right? We don't traverse or meet any node twice, right? It means that we go over all the edges and all of the nodes. So the time complexity, easily you can write order of V plus E, and V is number of nodes, or here it is number of tasks, and E is number of dependencies, okay, which is our edges. Okay, this is the worst case. Actually, we do always, all of them. But, if we have a cycle, it will be done, really sooner. We will detect, source, will be empty sooner than, we traverse all, vertices and edges. And what is it? This is actually time complexity. Let me erase this guy to make here.
I have a quick question.
Yes.
So, like, why would we return sooner if we had a cycle, right? We're only checking it.
But you mean, here also, if you have a cycle, we don't add in the sources, right?
All right.
Immediately, if we see that, the sources queue will be empty. Actually, we don't do any extra thing here, right?
Makes sense. Makes sense. Yeah.
Yeah. But it is. If we can, but actually automatically we detect here because the sources will be empty.
Exactly.
Yeah, and so this is our time complexity. What is the space complexity?
V.
So which data structure we used? We used the graph also in degree, right? So what is the size of this graph? As you can see here, we have, let's say V rows, right? And how many numbers we have here in all of these guys? All of these, X's, will be E, right?
Yeah.
So we have V plus E also for space complexity because this is for space. Okay, because, the size of our graph is V plus E. But if we wanted to use, let's say, the adjacency matrix, it would be V squared, right? The space complexity. That's the power of the adjacency lists. If we wanted to use adjacency matrix, assuming that we use, we don't use bit manipulation, right? Because for the adjacency matrix, because we have 0 and 1, we have lots of optimizations for adjacency matrix. I'm assuming we are using integers to store the 0 and 1s in the adjacency matrix. With that assumption, the space complexity, if we use adjacency matrix, was V squared because we need V rows and V columns. V is actually right now that actually is equivalent to N we use in this code. But actually for adjacency matrix, we can use integers and do the bit manipulation to handle that. We can decrease this to order of actually V also. But it doesn't make sense to do lots of the difficult things to decrease a little the space complexity. That's why adjacency list is really wise selection, and this is the optimum solution. And actually this is exactly a BFS pattern, but because you need to be fluent in making your graph, and you have to detect based on the question. Sometimes it is not really obvious like this. Sometimes we have some dependencies. If you see some dependencies and you see you can do this, model this like doing the graph, you should the topological sort pattern should be triggered in your mind. And I think it is one of the easiest patterns to detect. But the solution is a little long. But again, I'm repeating. If you use some functions like this we did for build graph, your code will be really short, and then you can make it really in the next step. But you have to know what this function exactly returns. The graph is a hash map, and unibly also is a hash map here, or we could use a simple array also. Okay, any question?